In this video we will be covering problem 1016, which deals with calculating the probability of a type 2 error. And there's a couple things you should probably know about type 2 errors before we start this. First, that understand you need to use a two-stage approach when calculating the type 2 or the beta error. In stage 1, you set up this rejection region in terms of what the book calls an unstandardized test statistic. So you'll see this will make more sense once we do it, but just know that there's two stages. So set up the rejection region, and then in stage 2 you find the probability that that unstandardized test statistic does not fall into the rejection region given a specific value of the parameter. And the problems you're going to be working on, the book will give you the parameter. The other thing, so remember that it takes two stages to solve it, and you also need to know that the probability of a type 2 error decreases as the alpha or the significant level increases. So they work in inverse. So if you've got a higher alpha, then the beta is lower. So if you go alpha from like 0.05 to 0.10, 5% to 10%, then the beta would drop. The other thing that causes the type 2 error to decrease is when you increase the sample size, the n, and you hold the alpha constant. So specifically when we're looking at problem 1016, it's asking us to find the probability of a type 2 error for the following test of a hypothesis. And we're going to eventually use the given of the p equals 1,5. Again, this is on page 167 of your textbook. But you can see right here I've got the hypothesis set up that p is equal to 0.2, and the alternate hypothesis is that it's not equal to 0.2. So given that, what we know from the problem is that the p is 0.2, the n or the sample size is 750, and the alpha is 0.10. And because it's not equal, we've got to do the two-tail test, because it could be off on the left side or the right side. So if we look up a z-score for the alpha of 0.10, remember we're going to divide it in half. So it's really going to be, I could put that in here, the z of 0.05. And I can even sort of work this in. Oh, what happened here? Open that font, put a sub in there, and make that a little larger so it's easier to read. And now I'm going to bring up table 3 from page 310 in your textbook. And given that we want it at the 0.05, that means we're looking for 0.95 here. And right here, with 1.6 in the row and 0.05 in the column, we've got 0.9505. If we go over 1, we're still in 1/6 row, and 0.04, it's 0.9495. So it's really right in between those two numbers. So it's 1.645. So that's what we're going to put in here. 1.645, the minus. And now, throughout this, we've got this standardized test statistic. The z equals the p hat minus p divided by basically the standard deviation, the p times 1 minus p divided by n. So we have a two-tailed test, so we're going to solve for p hat less than the left-hand tail and greater than the right-hand tail here. And so basically, to solve for p hat right now, we're going to do a little algebra. So again, if we go over to table 3, you can see that if I go to the point 3 here, and then go all the way over right here to point 8. So 0.38 gives us the 6480, which is what we have right there. So that is the probability of the type 2 error given 0.52 with the alpha of 0.5. Now let's recalculate this for part B, but instead of alpha at 0.05, we're going to use 0.02. So again, we've got 0.5, we've still got n for the 1,000, and the alpha of 0.02. And now what we need to do is go look for the z-score for that alpha at 0.02. So I'll bring up table 3 again, and basically it's got 0.9803 here or 0.9798, so it's kind of in between here. We could just call it 2.05 and we'd be okay. I mean, it could be 2.055 maybe, but for our purposes, let's just put it at 2.05. And again, we want to do the calculation now of the p-hat, and we're using the same z times the denominator plus p to give us p-hat. So let's do that. Equals the z-score times the square root of p times 1 minus p divided by n plus p is equal to, oh, it didn't like something in my formula here. Just 1 second. I think we're good there now, and that gives us the p-hat of 0.532. If I scroll down just a little bit, so the beta is equal to the probability of p-hat less than the 0.532 given a p of 0.52. So again, we're going to calculate the numerator for the z-score, which is equal to p-hat minus, and then it's the p, which is, well, let me do this. I'm going to put the 5.2 right here, make it a little easier. So it's equal to p-hat minus p gives us 0.012, and then the denominator is equal to the square root of P times 1 minus P divided by n of 1,000, and that gives us, if we reduce the number of decimals showing to 0.0158, and now we just take the numerator divided by the denominator, and that gives us, in this case, 0.79. Now I think that's a little bit of rounding there, so if I just actually typed in the 012 and the 0158 and then did this division, numerator divided by denominator, to give me the z, it gives me 0.76. So the probability of a z less than a 0.76, and if we bring up table there, 0.76, and we see 0.7764, which is what we have showing right there, which gives us the probability of a type 2 error when p equals 52 and alpha equals 0.02 is 0.7764. So from here, the alpha was 0.5, and it was 0.6482 or 80, and then when the alpha dropped to 0.02, this beta increased. So that's what we get for part C when it asks, describe the effect on B of decreasing A. So when we decreased the alpha from 0.05 to 0.02, the beta increased from 0.6480 to 0.7764. Again, sorry it took me so long on these. I hope it's helpful.